Get rid of that. Go from current slide. And maybe even turn on projector. What do you think? Now, announcements. We'll keep them brief. I think I told you last week that I thought the final exam schedule published was wrong. I checked with my boss on Friday, and he said, yes, it is wrong, but they're going to leave it since it was already published this way, so it was up to the instructor. So since it's up to the instructor, we are having class next Monday, okay? It's listed here as final exam day, but it was not on the college calendar, the academic calendar, the administrative calendar. That's the last day of class, not the first day of finals. So we will be having class today, Wednesday, and Monday, and I'll be giving you your final exam on next Monday, okay? It'll cover Chapter 4, which we're doing now, and get started into 5. There won't be much on 5, but I think you'll find 5 is probably easier than 4, but 4 is pretty easy, but it'll be that. And it'll only be 10 questions, about the same length as the others. You have a week to get it in. Unless any of you are graduating. Are any of you graduating this term? No? Okay, good. Then if you are graduating, you have to have yours in by Thursday because I have to have your grades in by Friday noon. Everybody else is the following Wednesday noon. So you have plenty of time to get it done. Okay. And it's easy test, as always, yeah, so I can promise you that. Okay. All right. Any questions on anything else? All right. Where we left off last time was on page, in Chapter 4, Integration, 4.5, Integration by Substitution, and we're on Theorem 1413, which is anti-differentiation of a composite function. And this is what they call pattern recognition, which yeah, it's a pattern and stuff like this, but it's still so easy to do a substitution. And since substitution works for the harder problems, it works just as easily for these problems. So I see no reason to really do this much unless you just see it and say, oh, okay, that's what it is. And if you're comfortable with that and it's correct, you can do it. Let G be a function whose range is an interval. Okay, so get this. G is a function whose range is the interval. Most of the time, we're used to that being the domain, but the range is an interval. And let F be a function that is continuous on I. And that basically means I is the domain of F, but the range of G. If G is differentiable on its domain, okay, and capital F, not little f, but capital F is the antiderivative of little f on I, that domain, then the integral of f of g of x times g prime of x dx, hey, we know what that is, don't we? That's just the chain rule. That's the chain rule if you're taking the derivative of f of g of x. It would be f prime. Okay, let's do it this way. Taking the derivative of this, it would be derivative of f, which is little f. That's what it just says here. Capital F is the antiderivative of little f, meaning little f is the derivative of capital F. So it'd be the derivative of this would be capital F prime, which is little f of g of x times g prime of x. So if you have something, you look at it and say, oh, that is the answer to a chain rule derivative, then I know what function that came from. You can just write it down like this. That's basically what they say. But here's what you really do. Let U be the innermost part. Let me phrase it a little differently. The inner part of this function f of g of x, okay, f prime. Find the most difficult part of the problem, the innermost part of that most difficult part, let that be u, okay? Let u be g of x, okay? Then figure out what du is. You know what g of x is. This is what you chose as the innermost part. Do a derivative of that. Then g du would then be g prime of x dx, which is exactly this. And then we have f of u du. And that's going to be the antiderivative of f. Okay? And that's what we're doing. This makes it sound really difficult. It really isn't. It's a pretty straightforward process. Okay? And the key is this. And we'll talk about that a little bit more. Okay? And as we do some examples. And they say examples 1 and 2. Okay, example 1 shows how to apply that theorem directly by recognizing the presence of f of g of x and g prime of x. Note that the composite function in the integrand has an outside function f, inside function g, and the g has its derivative, g prime, present also in the integrand. Okay? Blah, 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 a lot of words, but once you start doing them, I think you see they're almost a piece of cake. It's kind of like a little puzzle that's fun, okay? Can I say that? Calculus is fun? I guess we can. Okay. It really is. Okay. So here's example 1. I can tell by the fact that the slideshow didn't say 1 and 2. The book says 1 and 2. They're going to skip example 2. So we'll do example 1 first. Okay. Here we have, obviously, a product situation here. That's the first thing to look for. You have a product here, and you know how to take the derivative of a product, but the antiderivative of a product, the derivative of a product is two different things. This is only one, so you can't really undo that easily. So what we look for is take the bigger part, the more complicated part of the problem. That's obviously this part, okay? Take the innermost part of that complicated part, that's this part, and then look at what its derivative is, 2x. There it is. Hey, let that be my u, okay? Find the most complicated part of the problem, find the innermost part of that complicated part, and let that be your u. So, let me get my pen set up. Okay, let u equal innermost part, 2x, I'm sorry, I'm taking a derivative. Innermost part as written, don't take a derivative yet, be x squared plus 1. Right? Now, that's your first step. Next step is always then take its derivative. du is what? Write it in differential form. What would be derivative? Is what? 2x dx, perfect. And there you see 2x dx is right there. So what we have here then is the integral of, or antiderivative of, and what was this? This is my u, right there. So it's u squared, and this was my du. And I think I can do that. What would that answer be? Anybody? U cubed over 3 plus c, plus some constant c, right? That's it, okay? Now, are you through? Not quite, because your problem had x's, your answer has u's. Go back and substitute what u is, or you are, or whatever. I'm not good at math, English, okay? So this would be x squared plus 1, that's what u is, okay, cubed over 3 plus c. Okay? Now, if you might say, that can't possibly be that easy. Okay, I can read your minds, and you're thinking that very thing right now, right? Well, let's see. Take a derivative of it and see what you get. Derivative of this thing would be 3 times 1/3. The 3's go out, and that leaves you x squared plus 1 squared, because you reduce that by 1, times 2x. X squared plus 1 squared times 2x. That's exactly your integrand. Yep, that's it. That's the antiderivative of that integrand. Why recognize a pattern? Just do your substitution. Okay? That's why they call it a substitution method. All right. So let's see what they've got here. Now, believe me, they'll find little ways to make it more complicated. That's the job of a mathematician. I mean, the writer of math books, right, is make it a little more. We'll find that, but we'll find those are pretty easy too. So let's see. What do they do first? Let g of x. Oh, yeah, let's do this. Let g of x be this, and then g prime will be that, and then we have this. Why don't we just say let u be that? Not g of x, u, okay? It's so much easier, okay? Because this, you have to go through and see, well, then this is that, and then from this, you can recognize the integram follows that pattern. Oh, yeah. Oh, well, then let's make this a power rule. Do you find that easier to understand than let u be that? It just seems like to me, let u be this, go through, we've got it not. You don't have, same answer, but it just seems like this is a lot more esoteric. Maybe it's just me. I don't know. But it seems like this is going around your elbow to get to your ear. Just do a substitution. That's what we're going to do later. Now try using the chain rule. See, yeah, we did that already, and we found out that is exactly it. So, let's see what this is. Okay. That's the thing that's going to come up after example 2. So let's go back and do example 2. All right. Any questions? You all okay with what I did or how I did it? If you want to use pattern recognition, by all means do it. Yeah, it's perfectly fine. It's correct. But to me, this is so much easier just doing a substitution. Example 2. Find the integral of 5 cosine 5x dx. Now, this one, I think, yeah, you can almost look at that and tell the answer. But in case you can't, it doesn't hurt to do what would be, how would you approach it? I'll let you decide how you're going to approach it. Anybody? What would that antiderivative or integral be? Or break it down. Say again?
Just pull out the 5.
Okay. Integral of cosine 5x dx. Okay, that's sure a very legal, legitimate thing to do. And where would you go from there? Anybody? Wouldn't go anywhere, huh? Okay, you just sit right where you are, okay? Oh, Johnny comes lately, huh? Okay, here he is. All right, good deal. Now, where would you go from there, huh? With what? You may have said it right, I just don't hear well.
I said change the cosine.
Change the cosine to what? Oh, okay. All right. No one has an idea where you want to do next? Okay. Well, let me go back. It's not really undoing what Bill said, but just doing it the way we did before. What's the most complicated part of this thing? 5 really is not very complicated. That's why we pulled it out. So cosine is the more complicated part. And what's the innermost part of that part? Your 5x. So let your u be 5x. Now this is almost so simple you might not need to do this, but it doesn't hurt to do it. Let u equal 5x. Now, it's everybody's favorite for a substitution, let it be u. It doesn't, that's also a song, but that was never mind. We'll just use that. They use it all the time, but you don't have to. Let u equal 5x, then what's the next step? Once you got what u is, or u are, what did we do before? du. What's du then? This is page 297, 4.5 section. Example 2. What's du? Anybody? It's not that hard. 5 dx. Perfect. 5 dx. Okay? Now we can go back and plug this in up here with our substituted values. See, here's a 5 and there's a dx. This part right here is du. So what we have now is the integral of cosine, but 5x was u. Okay? Didn't know you were 5x. Okay. du. Now, I think we can do that one. Please tell me we can. What's the antiderivative of cosine u du? Sine u. Exactly. Okay? Okay? Because the derivative of sine is cosine. Plus what? Indefinite integral? C. Okay. Yes, in Spanish. Okay. So, now all we have to do is get us out of u's back to x's. Well, u is 5x, so we have cosine. I'm sorry. I can't. Duh. How dumb. Let's get rid of that. Okay. Sine of 5x plus c. Okay. And if you have any doubt, just take a derivative of this. Derivative of sine. Yes, we can do it. What's the derivative of sine?
Cosine.
Cosine, 5x. Then chain rule, derivative of 5x is 5. 5 cosine 5x. Yeah, that gives you derivative of c is 0. Okay. So absolutely that's it. So build way would have worked. It's just the antiderivative of cosine is sine, but then you have the chain rule 5x, it would be sine 5x over 5, and then the 5 cancel out, and you wind up with the same answer. So yeah, that would have worked too. I couldn't get anyone to tell me what the antiderivative of cosine 5x is. But if you put the u in there, in this problem, that just became really easy. There will be others coming up later when it's not quite so simple, but it's still just a couple little baby steps away from being that simple. Okay? See how that works? Sine 5x plus c. Okay. Let's move then to their gray box at the bottom of page 297. And this is what it's saying. The integrands in examples 1 and 2 fit that pattern exactly. Okay, exactly, there's a key word. You only had to recognize a pattern. Well, why not just make the substitution and then the pattern becomes intuitively obvious almost. Mathematicians like to say that anyway. You can extend this technique considering the constant multiple rule, and this is exactly what Bill was doing. If you have a constant front, pull it out front and see if you can go from there. Many integrands contain the essential part, the variable part of the g prime, but are missing the constant multiple. So what you do is just adjust it so you get it. In such cases, you can multiply and divide by the necessary constant multiple as shown in example 3. So I have a feeling example 3 is coming up. Any questions before we go to it? Okay. Let's find this indefinite integral. Now, what's my suggestion? Yeah,
Plus 1, u.
Yeah, x squared plus 1. Let that be our u. Perfect. Let u, and most of the time I sort of don't stand on formalities, but I think it's a really good practice to write this out. Let u equal x squared plus 1. Right? Then, and you always know the next step is what? Du is equal to little 2x dx. Perfect, perfect, perfect. Okay? Now we have a problem, Houston. Okay? Here we have a 2x dx. Up here we only have an x dx. So we don't quite have it right. Now they say multiply and divide, and that certainly works. Okay? But I find it easier, and I'm lazy, okay, is just because up here you have a x dx, not 2x. Let's make this an x dx. How do we do that? Divide by 2. Both of them divide by 2. And now we do have an x dx, okay? So now this part here is a du over 2. Boo hiss, okay? But the rest of it's fine. So this becomes the integral of, I'm going to pull out the 1/2 now, because you don't really need the 1/2 in here, so pull it on the outside. So now we're rid of the 1/2, and now we're just left with the du part. So we have u being x squared plus 1, so that would be u squared du with the 1/2 out front. And I think we've almost done this exact integral before. We just didn't have the 1/2 there. Let's just write down the 1/2. What's the antiderivative of u squared du? I know it was a long time ago, like 15 minutes. What was that? Antiderivative of u squared. U cubed over 3. Now, here I hang off the plus c for a minute here, okay? I'm going to write it in lightly, okay? Because I really don't want that plus c, okay? And this is going to be u cubed over 6, or 1/6 u cubed, plus 1/2 c. Well, if c is a constant, 1/2 c is a constant. So let's just make that our real constant, okay? Because it's just an unknown constant. Well, 1/2 of that is still an unknown constant. Let that be our constant, okay? Now, one more step. Our answer is in terms of u. We want it in terms of x. What would that be? What's our u?
X squared.
Okay, so it'd be x squared plus 1 cubed. Let's just put the 1/6 out front. I put really ugly. Let me see if I can make that a little cleaner. Okay. My pen. Okay, there we go. 1/6 x squared plus 1 plus c. You could leave it c over 2, but why do that? Just have it c. Well, let's take a derivative. C is what we get. This gives us 3 times 1/6 is 1/2 x squared plus 1 times 2x. Well, 2 is going to wipe out the 2 here, so that gives us an x dx. And what do we have? X open this thing squared. X squared plus 1 squared. Yeah, absolutely. That gives it to us. Make sense? So my little rule is find the most complicated part of the problem and then do the innermost part of that most complicated part and let that be our u. Sometimes it may not work, but at least most of the time that's going to be a good start. And then after that you may find other things you have to shift around or do to get it to work, but it usually does. Okay? Let's see how they did it. I have a feeling it's going to be slightly different, and if you like their way better, by all means do it. Okay? You're not stuck on just what I find easy. This is similar to the integrand given in example 1, almost the same, except it's missing the factor of 2. Well, you wouldn't always have done 1, so you can't say that. So recognizing that 2x is the derivative of x squared plus 1, the innermost part, the most complicated part of the problem, you can let your g of x then be, or I'd say u equal x squared plus 1. Okay? And here's where they do the multiplying and dividing and shifting things around, which is fine. It's perfectly good. So here they put the x squared plus 1 squared out front, and then move the x back here with the dx, and do 1/2 of 2x, which is x dx. Okay? Perfectly good. Okay? Now what they do is pull the 1/2 out front, just like we did, and then the rest of it is exactly what we got. With this 1/2 out front, this is exactly example 1. There's your f of g, and there's your g prime. Okay? Do I want to go through and do all that? No, I'd just rather let u be that and go with it. Okay? But this does give it to us, and you have 1/2. Now you see how they got around the c part. They did the antiderivative of that right here with the 1/2 and let the plus c be at the end. That's probably a little bit neater way of doing it than kind of ignoring it and then throwing it in at the end. I guess that's a little better. So they have their strengths here. So that's 1/6 of x squared plus 1 to the cubed plus c. Okay? Now, actually great, really good. I just like seeing the u squared and then thinking, oh, that's a power rule. I don't always see an x squared plus 1 squared and think, oh, that's a power rule of this as long as you do this, as long as you do that. But once you got the u in there, it's obviously just a power rule. So I found the other way a little simpler, but either way, get the right answer. As long as you take all the right steps, that's the key. Just do the right thing and you'll get the right answer. Okay. Now, that was example 3, I'm pretty sure. Yeah. Now, any questions on that before I leave? Okay. The next subsection here is change of variables for indefinite integrals. Guess what? That's what I've been doing. Okay? With a formal change of variables. So you have to wear your tux and, yeah, never mind. For this one, completely rewrite the integral in terms of u and du. To me, it's easier than g of x and g prime of x, but I don't know. Maybe it's just me. Although this procedure can involve more written steps than pattern recognition, I kind of doubt it. It is useful for complicated integrands. It is useful for simple ones too. The change of variables technique uses the Leibniz notation for the differential. Fine. That is, if u is equal to g of x, then du is g prime of x dx. Okay? If I don't even put the g of x in there, so we've been doing that. Okay. Oh, I'm sorry. They have all that written here. With a formal change of variables, you can rewrite the integrand by, in terms of that, we just said it. Although this procedure can involve more written steps, which I don't think it does, but I guess it could. The change of variables technique uses Leibniz notation, so if you have, see, I never put in the g of x anyway. If you just put u equal whatever that complicated, that innermost part is, you don't ever call it a g of x, then du is the derivative of that complicated part without ever calling it g prime of x. So to me, their step puts an extra step, their technique. But if you see it better this way, by all means do it. But if you get this done, then you're then just integrating at f of u du. And if this is something you can integrate, do it. Okay? And if that involves some constants out front or something, then put the constants with that, but leave the c alone. Just put the c at the end. And it works out really nicely. So here's example 4. Where would you go with this one?
U equals 2x minus 1.
Second?
U equals 2x minus 1.
Excellent, excellent. Let u equal the innermost part, the most complicated part. Well, the most complicated part is the square root, obviously. So 2x minus 1. Then, always your next step is?
Du.
Du is equal to?
2.
To what? Dx. Oh, write it as a, what do you call it? Differential. Differential form. And also write it, that Cedric's here. Okay. That's the other part of the problem. Okay. No problem. Okay, got it. All right. We're in Chapter 4, Integration, 4.5, Integration by Substitution, page 298. No, 299, example 4. Okay? So there we have our du is equal to 2 dx. Uh-oh, SpaghettiOs. We don't have a 2 dx up here. All we have is a dx. So therefore, what I like to do is just divide both sides here by 2. Now we have a dx. Okay? So we're going to write this, so this dx here is the same as du over 2. Okay, so I'm going to write that integral, but I'm going to pull the 1/2 out and then do the integral of, now the other thing I don't like to do, I think you've heard me say before, is I don't like to try to integrate or differentiate a radical. So what would you do with the radical?
Make it u to the 1/2.
Exactly. Write this as u, which is the 2x minus 1, u to the 1/2 du. Because the du is dx over 2. I'm sorry, dx is du over 2, so you got the over 2 out front, and now you have that. And I think that even we can do that. What's the antiderivative of u to the 1/2? Anybody? Anybody? U to the 3/2 over 3/2 would be perfectly fine, but that's the same as times 2/3, right? Yeah. Okay, that's the same. Take the derivative and see if derivative of 2/3 of u to the 3/2 is u to the 1/2. Yeah. Okay. Now we're going to keep this together and then put our plus c. I like their technique of doing that. Well, you don't have to worry about the constants. Okay. So here we see that the 2's can cancel out, divide away actually, and this would be 1/3. And what is, here's Taylor. All right. All right. Again, we're on in Chapter 4, Integration, 4.5, Integration by Substitution, page 299, Example 4. We've got it this far. So 1/3, and what is your u? 2x minus 1 to the 3/2 power, I can't write, plus c. That's all there is. I'm sorry. Seems like it should be harder than this, doesn't it? But it's not. I'm sorry. I've tried to figure out a way to make it harder, and I just can't do it. It's okay. Let's just check our answers and see. 3/2 times 1/3 is, the 3's cancel out or divide away. You have 1/2 of 2x minus 1 to the subtract up 1 from this. You get to the 1/2 power. Then do a chain rule times 2, and the 2 wipes out the 1/2. Yeah, you got exactly what we got there, if you put it back under a radical.
Dr. Fallon, did
Yes.
you mention some scenarios in which your method would not work?
Oh, yeah. We'll find plenty of those.
Okay.
But all we're going to be doing now are those that will. You have to do adjustments like moving a 1/2 out front and stuff like that. That's all we're going to worry about now. You asked for it, you got it. So what if this was a squared here? This won't work then. Okay? So then we do a different kind of substitution. That happens to be a trig substitution. That's the next course. So hang on, we'll be there. Okay? But it'll take us a while. The ones you have now will be able to do this. Okay? But yeah, if that was a 2x squared under there, no way you're going to get this kind of substitution, simple substitution to work. There will be other ways. Okay. Good look ahead. But not yet. Okay. All right. And that's, they do this one. So let's erase what we've got and see if they got the same answer. And they probably do it a little differently, but let's see. First, let u be the inner function. They did it. Hey, they're leaving out the g of x now. Good. Okay. So this was 2x minus 1. Then your du is just simply 2 dx. Always write that, the du, in differential form. And then we want to plug back in here, but we can't quite do it because there you have a 2x, here we have a 2 dx, and here we only have a dx. So let's see. But they did it without showing they did it. they did a dx equal du over 2, and let this be square root of u. And then why in the world did they put it square root of u? Write it in power notation, not in radical notation. And they do write the u. In fact, this step here may be a little clearer for you. If you didn't like my, why did he take that 1/2 out? Well, this shows you why. You substitute exactly. With u being this, then this is square root of u, dx being du over 2, then this is that, and this is that. Exactly. And then you pull it out front and write that in power notation. And you're right at the same place we were. So if the way I was doing it was skipping too many steps, do it this way. Works perfectly fine. And that we know the integral is 1/2 of u raised to 3/2, up it by 1, divide by that, which is exactly what Griffin was doing. But I just found it easier to go on and flip that over, because dividing by a fraction is multiplied by the reciprocal, and make that. Well, they didn't even show that part. So to me, it would have been, if you're going to do this, show the next step, and that becomes a 2/3, 2 divided out 1/3, u to the 3/2 plus c. Good deal. Any questions? Oh, and then they write it. Oh yeah, plug it back in, because your original problem with an x is you need to give the answer in x's 2 in terms of x. So that's 1/3 of 2x minus 1 to the 3/2 power plus c. Now, actually, if they went back that far, and they should have, well, the original problem was in radicals, so you could have gone back and said this is 1/3 of 2x minus 1, the square root of 2x minus 1 cubed, either the cube on the outside or inside, either one. I think we've talked about that before. They don't do that, but this would be okay too. I want to just 1/3 square root of 2x minus 1. Now, that takes care of the divided by 2. How about that cube? You can either write the cubed in here, inside the radical, or, plus c, or you could write as 1/3 the square root of 2x minus 1 cubed with the cube outside the radical. Either one of those will work. Perfectly correct. But I'm with them. Why go back to this? I prefer power notation over radical notation any day, whichever way. And this is perfectly good this way, and it doesn't have two different ways you could have written that. Okay, so. And they leave it that way. So, they have some guidelines here, but they've skipped example 5, so let's go back and do example 5. All right. Now, this one happens to be also at larsoncalculus.com. You can go there for an interactive version of this type of an example. So here's what we've got now. Find the integral of x times the square root of 2x minus 1 dx. Okay. Where would you do this whole? This is, okay, you're asking for others that were a little more complicated. This is one, okay? This is going to take a little bit of maneuvering here, but it's all legal in most states anyway, okay? So what are we going to do? What would be your first gut reaction?
Let u equal 2x minus 1.
Perfect. That is the most complicated part of the problem is the radical. Innermost part of that is that. So let u equal 2x minus 1. Okay. We're going to come back to that one. Okay. Then, what's next? du is equal to, second, not quite, 2dx. Perfect. You see? Right? Everybody? Okay. 2dx. Uh-oh. We don't have an x down there. This part is taken care of with the u. This part is taken care of with this. I think I am going to divide both sides by 2. Okay, or you can do it the way the book did it. Fine. Okay. But what do you do about that x? This is a little tricky, but it's true. Here you have an x, don't you? Solve for it. So what would we do? Anybody? Add 1 to both sides. So so here we have a different then going in this direction. Then u plus 1 is equal to 2x. And I got one more step. I want to isolate the x. So we, help me, divide by 2. So there's what my x is. Whoa. So let's see what we've got now. We've got the integral of, okay, if it's okay with you, well, if it's not, I'm still going to do it. I'm going to pull this 1/2 on the outside. Is that all right? Because x here is this laying with the 1/2. The integral's not going to worry with the 1/2, so I'm going to pull it on the outside. So this 1/2 goes on the outside, and that gives us a u plus 1. There's the x. And then we have here, we'll rewrite this, of course, as help me. Okay, 2x minus 1 to the 1/2 power. That's your square root of that. And then your dx from down here is du over 2. I just, wait. You had me say that. Do that, write it. It's right, but it is 2x, that to the 1/2. But what is 2x minus 1? U to the 1/2. And then my dx is du over 2. Well, I just want the du here, and then we'll put this over another 2, so this makes it over 4. Notice the sleight of hand we did there, okay? We did all sorts of manipulation there, okay? One of these 2's comes from x being this part, and the other 2 comes from dx being du over 2. So both of the 2's come out to be over 4. That looks a little messy too, okay? Except that we can distribute that one. Now, let's think about this. Here, that you you can't distribute a power that's not a radical, not to the 1/2 power, over what's here. That would be terribly messy. You could make this the square root of x squared and then distribute that in there, but that just makes the problem even more complicated. But here you can distribute, because this is a monomial to the 1/2. This was a binomial to the 1/2. Really hard to do anything with that. But here with the monomial to the 1/2, that's not bad at all. What would that give us? The 1/4 is still out front. The integral of, we haven't taken the integral yet. What would this be?
U to the 3/2.
U to the 3/2 power plus u to the 1/2 power du. Now, if you can do those with one integral, fine. If you take splitting them into 2, fine, split them into 2. Can we do it with just one? You answer me. Antiderivative of u to the 3/2. Anybody? Help me, somebody. U to the 5/2 times
2.
2/5, perfect, plus antiderivative of u to the 1/2. We've done that before, haven't we? Anybody?
It'd be 2/3 u to the 3/2.
Okay, u to the 3/2 times 2/3. Perfect. And then we'll put our plus c out here. I like the way the book does that. Get it out there and leave it alone. Okay. Okay, this is a little messier, but still doable. Okay, now notice both of these have a 2 in them, so we can divide up both of those 2 into that 2 and leave us a 2. So we've been monkeying around with that 1/2, 1/4, 1/2, you know, going back and forth. We can't make up our minds. But this now gives us 1/10. And let's go on and plug in. What is u? What are you? I don't know. What are you? Okay, never mind. 2x minus 1, right? So this will be 2x minus 1 to the 5/2 power, because we pulled out the 5 to go with the 2 and gave us a 1/10, plus, and here we'll still have this 1/2 times 1/3 would be 1/2 times 1/3. It's 1/6 2x minus 1 to the 3/2 power. And then we can do our plus c. Now, you mean to tell me if you take derivative of this, you're going to get that? Are you kidding me? Let's see. That's what it says. Antiderivative, derivative, you know, it should be it. 5/2 times 1/10 would be 5 going to 10, that's 1/4, right? Those are 2 you got. 1/4 of 2x minus 1 to the 3/2 power. Okay, be 1/4 2x minus 1 to the 3/2 power plus 3/2 times this would be 1/4 2x minus 1 to the 1/2 power. Okay, and the plus c would disappear. So you can pull out a 1/4 2x minus 1 to the 1/2 power, and that would leave us with a 2x minus 1. If you pulled out the 1/2, it leaves you 2 halves here, plus 1. Well, plus 1 minus 1 is going to be 0, 2x, hey, and okay, I haven't done the chain rule yet, times another, oh, or did I? Yeah, times another, okay, times another 2. Okay, derivative of this would be 2. Okay, so 2 and 2 wipes out the 4. All we got left is x times that, and that's exactly what we have there, because x, 2x minus 1 to the 1/2 power is a square. Almost harder to check than it was to do the problem, but if you're careful with it, you see that does give you that answer. So this was all checking. This was your answer. So I'll wipe out the checking so it won't confuse you any more than I already have. Okay. But that was your answer. And sure enough, that's, I hope, what they got in the book. Let's see. This is example 5. 1/10 2x minus 1 to the 5/2 power plus 1/6 2x minus 1 to the 3/2 power plus the. Any questions on that? Any part that was ambiguous, too much of a shell game, you know, confusing? Everybody understood? Earth this class, come in, please. Never. Okay, all right. So let's move on to, I think example 6. Whoa, wait. Let me see. I think example 6 is missing 2. Yep. So let's do example 6. All right. Okay. Example 6. Find the integral of sine squared 3x cosine 3x dx. Now, this one, you might be able to do it without it, but the way we've been doing it, we're probably going to have 2 substitutions here. So you're probably going to use u and something else, not x, okay, and not u again. But what would be your first inclination here? Anybody? Or you might use one substitution and then do a, what do they call it, recognition, pattern recognition or something. I don't know. Or maybe you can just do a pattern recognition as is, but anyway. Tell me what your first step would be.
Would you let u equal 3x?
That's what I would, okay? Just to keep it simple. Okay, I won't put the other part in there. Let u equal 3x. Then, what's always the next step? du is equal to 3dx. Got it. Okay. Obviously, we don't have a 3dx up here, so let's make it a dx by dividing by 3. Okay. So we got what our dx is. This is your 1/3 du. Got it? All right. So what we have now is, this will be 1/3. I'm going to bring that 1/3 on the outside. 1/3 the integral of sine squared u. Ooh, goodness. Okay, it'll come back. Okay. U is your 3x, cosine u du. Okay. Now, at this point, if you say, oh, I know the answer to that, we can do it. Or if not, we can still take it one more step. If you were going to do a substitution, what would you do with that? And if the big problem here is what letter to choose next, just say V, okay? U, V, W, X, Y. We got several left. So let V equal, what would that be then?
Could you let it be equal to sine u?
I would do that, sine U. Okay. Then, dV is equal to, it's dV, not VD, never mind, we won't go there, okay? Equal to what?
Negative cosine.
No, derivative of sine is positive cosine, okay. So cosine U, differential form, du. Perfect, and now that's exactly what we've got here, okay? So now we can rewrite, and this will be 1/3 the integral of what? I'll let you tell me what to write there. V squared dV. Got it. Got it. I think even I could do that one. Okay, what would that be? 1/3. But I'm not. I'm going to let you do it. Antiderivative of V squared. V cubed over 3 plus C. All right. So this would be 1/9 V cubed. But we got to substitute what V is. L plus C. And what is your V? 1/9 of places here. All right. We're in Chapter 4, Integration, 4.5, Integration by Substitution, page 300. Okay. And what was your V?
Sine U.
So this will be sine cubed U plus C. Okay. But what was our U?
3x.
All right. So it's 1/9 sine cubed 3x plus C. All right. I think we may have it. Let's see what they got. 1/9 sine cubed 3x plus C. Good for them. And then you can check by differentiating this. Yes, I wanted to do that. So this one isn't really so bad. This would be 3 times 1/9 would be 1/3 sine squared 3x times, first a chain rule on the sine, cosine 3x, and then a chain rule on the 3x, another 3. That 3 wipes out the other one, so you have sine squared 3x, cosine 3x. And that's exactly what we had up there. Not bad at all, was it? Make sense? Substitutions. Fun, right? Oh, can we say that? Yeah, it is. All right, so there's example 6. I think we're ready now for the guidelines, as if we haven't been using them. So the steps used in integration by substitution are summarized in the following guidelines. Okay? Choose a substitution U is equal to G of X. Why even introduce a G of X in there? Find a U. Usually it's best to choose the innermost part of the composite function, which the composite function is the most difficult part of the integram. The innermost part of the most difficult part of the integram. Okay? Such as the quantity raised to a power or the root taken or whatever. Okay? Now, once you chose U equal whatever that innermost part is, then do the du is whatever the derivative of that is, written in differential form, so you don't do du dx, you do du, whatever its derivative is, dx, in differential form. Then rewrite the integral in terms of the variable u. Integrate, find the resulting integral in terms of u, in other words, integrate, I think is what that is. Then you go back and replace the u by whatever your substitution was, whatever the innermost part, to attain the antiderivative in terms of x, and check your answer by differentiating, especially if it's pretty easy. Okay, if it was harder than doing the problem, you might say, I'll trust it, you know, but that's up to you. Okay. Now, they have a little blurb at the bottom. Let's see if they print it here. No, they don't. Let me read that little blurb at the bottom. So far, you have seen 2 techniques for applying substitution, and you'll see more techniques for the remainder of the section. Each technique differs slightly from the others. You should remember, however, that the goal is the same with each technique. You're trying to find the antiderivative of the integrand. Okay. All right. So we've been doing the general power rule for integration. Nothing new here. That's what we've been doing. So one of the most common U substitutions, how are we doing on time? Okay, we got plenty. U substitution involves quantities in the integrand that are raised to a power. Okay? Because of the importance of this type of substitution is given a special name, the general power rule for integration. Okay, I didn't know it was given this special name, but that's what it is. G is a differentiable function of x, then whenever you have that g of x raised to a power followed by g prime, then you know you can do exactly what we've been doing. As long as the power was not a -1. Because if the power was a -1, what are you dividing by here? 0. And we usually don't do that. Okay? In fact, we never can do that because it's not a line. So we'll have a new rule coming up. That's why we're going to hit chapter 5 before we finish the term. What to do if that is to the -1. Some of you may know already. Equivalently, if u is g of x, which is what we had it was, then the integral of u to the nth du, because that's what that thing was du. Du would be g prime of x dx. That's exactly what you got there. Du to the n plus 1 over n plus 1 plus c. And we go from there. As long as n is not minus 1. And we'll see what to do if it is. Okay. Again, I don't know what's any different about these. We're the same as we've been doing. Where would you, I wish they didn't even do this. Okay. We'll just pretend that's what we were given. Where do we go? Where would you approach? What would be your start? I'll put the let down. Okay.
U equal 3x minus 1.
Yes, the innermost part, the most difficult part of the integrand. Okay, let u equal 3x minus 1. Then, always follow the let by a then. Du is equal to 3dx. Okay? And look at what we have here. We have a 3dx right there. That is your du, just as is. Okay? So what's your new integral? U to the fourth du. And I think even I can integrate that. What would that be? Anybody? U to the fifth over 5 plus some c. So what we do is go back and plug in what u is, and that would be 3x minus 1 over 5, or 1/5 of that. Oh, to the fourth power. No, to the fifth power plus c. Another way to write it is 1/5 3x minus 1 to the fifth power plus c. Either way you want to do it. They usually like to pull the 1/5 out front. Okay? You can go through that route. That's exactly what we did. It's why not follow the same pattern we've always followed? It's just that simple. So let's see. Any questions on it before I erase it? Okay. All right, so they're just doing it without, they're writing the u's on top rather than underneath. That's a big improvement, isn't it? Okay, it's the same deal. I guess this is what they call the recognition part, just recognizing that as a u to the fourth, and that's your du because it's 3x, derivative of that would be that, and that would be u fifth over 5. So they went straight to the answer. So in that sense, they are leaving out some steps. And if you're comfortable doing that, by all means do it. It's fine. Just make sure it's right. Okay. Any questions? All right, here's another one. And again, maybe that's helpful to you. I'll erase it in a minute. Where would you go with this one? Oh, my goodness gracious. What are we going to do here?
Same as the last.
Say again?
Same as the last.
Okay, and how would you do? Where would you start?
Use the next square plus.
Okay, that is exactly right. But that's not the only way you can go on this one, folks. Okay? What you could do is spoil this. Multiply it out, and you have a polynomial, and it's real easy to integrate. But this just happens to be that the derivative of this is that. And because it is, this makes it easier. So like you said, let u equal x squared plus x. Okay? That is the more complicated part of the deal here. Now, if when you took the derivative, which is the next step, which is, then du is equal to 2x plus 1, which is exactly this dx. Okay? Now, because that worked out that way, fine. But what if this had been a 2x plus 2, or a 2x plus 17, or anything else? This isn't going to work. So then you multiply them together and just do it that way. But this just happens to be one that this is the derivative of that, so this makes it really easy to do your substitution, which is the integral of u, me? No. du. And I think I can do that one. What is that?
U squared over 2.
U squared over 2 plus c, and then the u is x squared plus x over 2 plus c, or 1/2 of x squared plus x plus c. Okay. Oh, squared. You're right. Oops. Yeah. Okay. Now, if we had multiplied this out and gotten 2x cubed and then all the rest of the thing, that would have been another 2x cubed, 2x squared, and that would be 3x squared plus x. I think it was what, yeah, this then. Then you integrate that. You certainly could do that, and you'll get an answer. And then it just happens to be that that answer would be the same square. Okay? But this is a little bit easier, but the other way is not bad at all. So you didn't have to do this way, but just because this derivative of this is that gives you an easy way to do this problem. All right. But again, it's not the only way. And it might be, if you're very good about it, you saw that is exactly the du. The 2x plus 1 is exactly the derivative of the x squared plus 4x. Okay. So that would just be x squared plus x squared over 2. And now they're putting the over 2, not pulling out the 1/2. I don't know. They're not very consistent, are they? Here's another one. So let's not do it this way. Though you can, if you see it, what would you do on this case? What would be your substitution? If you chose to do substitution. Second? Help me, somebody. Let u equal the innermost part of the most complicated part of the problem. This isn't very complicated. That is complicated. It's got a square root, and it's got a binomial in it. So let u be the innermost part. X cubed minus 2. Then du is equal to 3x squared dx, which is exactly that part. Okay? So what's our original integral? But now written in terms of u's rather than x's.
U to the 1/2.
U to the 1/2 du. Perfect. And what that integral, what would that be? 2 u to the 3/2 plus c, which would be 2 times x cubed minus 2 to
That one was over. That was over 3, wasn't it, Dr. Fowler?
I'm trying to see.
Over.
Oh, yeah, I'm sorry. Oh, 2/3. Okay. So that'd be 4/3. This to the plus c. Sorry about that. Yeah. Whenever you do the integration, you've got to divide by the u power, which is multiplied by the second. That'd be 4/3. That's ugly. That's really ugly. Let's first put a line in there and take out the 2. Yeah. 4/3. Yeah, that's it, I think. 4/3 x to the 3/2 minus 2 to the 3/2 power plus c. Okay? And let's see how close they got. Now, they're just doing their, I guess, recognition by saying, hey, this on the outside is exactly the derivative of that on the inside, So move it over to the dx part, and you've got that. That would be u to the 1/2 antiderivative of that is u to the 3/2 over 2/3, over 3/2 or times 2/3 plus c, and then take that part and plug back in. How did I wind up with a 4 up there? I don't.
We put an extra 2 in there, I think, at the end.
Yeah, I'm sorry. I shouldn't have done that. I think I did part of it and then didn't do the whole part, and then I don't know what I did. But yeah, 2/3 x to the 3, x cubed minus 2 to the 3/2 power plus. Good. Sorry. Get to going too fast sometimes. But we got another one coming up. Oh, my word. I hate for them to do half the hardest part of the work for you. What would you do with that? Yuck. Where would you begin? Yeah, do the bottom. Let u be, what do you mean by that? It's what? 1 minus 2x squared. Perfect. The innermost part of the most complicated part of the problem. Then du is equal to negative 4x. And that's exactly what you got. Oh, dx. I left that off. It's exactly what you got in your numerator. So this becomes the integral of du, which is the minus 4x dx. That's the du over, and what's this? Over. In the military, that means you're supposed to answer. Okay. Over. I didn't say out. I said over. Okay. U what? Squared. Perfect. Now, I don't like integrating denominators, so what do I do? Okay, I think we're right. Okay, okay, du. Okay, u to the minus 2 du. Exactly. And I think we can do that, can't we? What would that be? Or can we?
It'd be negative u to the minus 4.
Yes, plus c. Now, you can't do it if the minus 1's in there, but you can have a minus 1 out here. If this was to the minus 1, you cannot use the power rule, because then you'd be dividing by 0. Does not work, but u to the minus 2 does work, and that's exactly right. So our last step would then be
Minus 1 over, substitute for u.
Yeah, 1 minus 2x squared plus c. That's it. That's the answer. Now, you can go back and check all these by taking derivatives. I'd rather not, but you can. Okay, it's perfectly fine, and it will work. Okay? Good deal. Let's see what they did. Let me erase my scratch. Remember, that's the answer we got, and this is what they got, which is that, which is minus, yes, same thing. Make sense? I think there's just one more of these. Okay, let's do this one. This one you might, just looking at it, be able to do it, but if you're going, yeah, I'm sort of this mindset. Maybe it's just because my wife says I always do things the hard way, you know, and maybe once you get something that works, don't fix it. If it works, it ain't broke. You know, don't fix it, okay? So, what would be your let's just ignore this, okay? Let u equal what? cosine x. Okay? The most complicated part of that is the squared part, and the innermost part of that is the cosine. Then du is equal to minus sine x dx. Don't forget the dx there. Always have to have a dx with any du. Okay. Now, we don't have that. We have a positive this. So let's move the minus sign to the other side. So this thing right here becomes a minus du. Right? Well, let's take that minus sign and put it out front, minus, and then your integral becomes u, help me somebody, u squared du, with the minus out front. And we can do that one, can't we? Negative anybody? Antiderivative of u squared? U cubed over 3. And then your plus c. And then plugging back in, your u was that, minus cosine cubed x over 3 plus c. Sorry. All right. Yep. Now, they doing, I guess, what they call their pattern recognition, just jumped straight to the fact that this was the minus derivative of that. So they put that in there. But if they put that in here, they have to put one out there to get it back, so you haven't changed the original. And that gave us exactly what we got. Okay. The only difference I can tell, they put the u's on top rather than on the bottom. I mean, they're still writing them down, but they're just saying if you can see it without doing the substitution, you can certainly do that, as long as all the steps are right. And that's exactly what we got. All right. So that was example 7. Okay. Now, what's that? Oh, sure. Okay, I'm sorry, I went too soon. They do have a little blurb at the bottom they put here just for Chuck. It says, some integrals whose integrands involve quantities raised to powers cannot be found by the general power rule. And then the first one they gave can, and the next one they give can't. Okay. I thought they were going to show this on the slide, but they don't. So I'll write it in for you. This one, the integral of x times x squared plus 1 squared dx. Power rule works like a champ here. You have to do a few manipulations with the derivative of this. The innermost part is 2x. If you have an x there, you can pull 1/2 out front. That'll work perfectly fine. Okay? But, on the other hand, this integral, x squared plus 1 squared dx, will not, because you don't have an x out here to work with. You've got to have at least the x to work with. This one would require a trig substitution, which is Cal 2. Okay, so don't worry about that yet. Okay? Oh, no, it doesn't. Because what you could do with this is square it. Okay? Just square it. And that'd be x to the 4th plus 2x squared plus 1. And you can integrate that. So no, you don't need a trig substitution. It still works, but that's more complicated. Okay? This one you could do the same way. You could square that thing and multiply it by this, and you get the same answer you would if you do your substitution. It's just a little more work. Okay? Second one, you got to do the work. The first one, you can do it without it. Okay. So don't try to reinvent the wheel when it's an easy thing to take care of. All right. Everybody finish this slide? So change of variables for definite integrals. Okay. What we just did will work with definite integrals, but remember, because your original, a definite integral has limits on it, right? Those are limits for your original variable, usually x, okay? Once you change to u, you can't use those same limits. So what do we do when that's the case? Okay? When using the u substitution for definite integral, it's often convenient to determine the new limits of integration for the variable u rather than taking it all the way to finding u, converting back to x, and then plugging in those. That's just extra work, okay? This change of variables is stated explicitly in this next theorem. If the function u is equal to g of x has continuous derivative on the closed interval a to b, and f is continuous in the range of g, okay? Because f is using as its domain the range of g, then the integral from a to b of f of g times g prime, which is exactly what you get from a chain rule of a composite function. And if you have exactly that as your integrand, then you can, rather than coming through and getting the u and then going back to x, just change your, and this looks like it's a really hard to remember. It really isn't, okay? When you're changing from x to u here, use the same thing. If x is equal to a, which is what this is saying, when x equal a to x equal b, remember that's what the limits are, the ends right here. Well, if x is equal to that, and you already have what u is g of x, then plug in the a here, and that's the bottom integral here. Plug in the b up here, and that's your top. These are just a function. Plug in a value. The a and the b, you get values. Put those as your new, and then you don't have to back up and go back to the x again. You can just solve it from there. And it's really easy, okay? Easier than indefinite integrals where you have to go back. So let's do this one. All right. Forget about the limits for now, okay? Just worry with doing the, well, we don't go straight to an integral. What do you do first? Focus on that integrand. Hint. I'll write the first word. Let.
U equal x squared plus 1.
X squared plus 1. Seems like we've had this one, haven't we? Seems like maybe there's not enough problems. We have to just keep reusing them all. Okay, anyway. Then, once you do your let, then always follow it by then. Then, help me somebody. Du is equal to 2x dx. All right. And now we go through the same thing we always did. This one only has an x dx, not a 2x dx, so we will divide both sides by 2. And now this thing right here that we got, x dx, is exactly 1/2 du. I like to just sort of do the, okay. Now, what we're going to do, this becomes the integral, just like before, of what? I'll put the 1/2. That's out front now. U cubed du. Okay. But what are we missing? We're missing our limits. Okay. Well, we can't put 0 and 1. Not allowed. because those are the limits for x. So what we do here is when x is equal to 0, what is your u? 1. So that would be u going from 1 to, and when x is equal to 1, what is your u? 2. From 1 to 2. And guess what? At the end, you don't have to go back to the x's again. The definite integral's so much easier to do. What's your antiderivative of u cubed?
U to the fourth over 4.
U to the fourth over 4. And we're going to evaluate that from 1 to 2. Because that's what u is or are or whatever. Okay. So I'm going to pull the 1/8 out. Okay. And then get out of there. Okay. 1/8 out, and then I'm going to plug in. What is 2 to the fourth?
16.
16 minus 1 to the fourth. Well, that's a hard one. 1 to the fourth. 1. Okay, good. So this will be 15/8. That's it. Don't have to go back to x's again because you changed your variables, the limits to the limits for u. So just do the integration in u, substitute in u, and be done with it. Okay? Oh, good. I was looking on the wrong page. Said, how did they get that answer? Okay. All right. Or they say, if you wanted to, at this point, when you have this answer, go back and plug it in. Instead of u, do x squared plus 1, raise it to the fourth power, and then plug in your 0 to 1. Yeah, I want to do it that way. Way more complicated. Just change the variables as you go. Change the limits of the definite integral as you go. And you got it right. All right, let's see how they did it. Can I erase? May I erase? I know I can. Okay. So let's see. To evaluate this, let u be the innermost part, the most complicated part of the integram, which is x squared plus 1. Then your du is 2x dx, okay? And because you don't have a 2x dx, before substituting, determine the new upper and lower limits of integration. The lower limit when x equals 0, u is equal to 1. The upper limit when x equals 1, u is equal to 2. So now, and by the way, folks, they're not always, if that differs by 1, these are not always going to differ by 1. Don't even make up a new rule. Say, oh, I just have to increase it by the same number. No. You have to plug it in both times. This just happens to work that way. And I'm so glad they wrote that twice. Oh, yeah, I see what they did. They took out the 1/2 in front and the 2x in here. So that's what they did. That's how they like to do it, and it's perfectly fine. It does the same result that we get. Okay? And that would be 1/2 the integral from, now that you change the du, you change your limits from 0 to 1 for x to 1 to 2 for u. That would be u cubed du, and that would be u fourth over 4, but you evaluate that from 1 to 2 rather than from 0 to 1 because it's no longer x, it's now u, and that gives us, okay, they did it that way, which comes out with the same answer, 15/8. What they did was I pulled out this and made it a 1/8 out front and then plugged in just these things for the u's. They actually evaluated this at 16 fourths, which is 4, minus 1/4, which is 1/4, so that made 15 fourths times 2, 1/2 is 15/8. Yeah. I love my fractions, but I don't love them that much. So if I can just pull them out to begin with, that's easier. Okay, any questions on that? Any way you do it, as long as all the steps are right, you should get the same answer. Okay. Now, what they then say here is at this point, if you hadn't done this, if you left it as an indefinite integral and then plugged back in x squared plus 1, excuse me. Y'all awake yet? Okay. I would never have done it if I made the change of variables. I'm going to plug them in. But if you hadn't made the change of variables and went back to your x's and used the original variables, 0 to 1, then you can plug these in as well. And you see it really worked out the same way. If you plug in a 1 here, that's 1 plus 1 is 2. 2 to the 4th is 16. 16 over 4 is 4. 1 over the and then plug in a 0 here, it would be minus 1/4. You get the same answer. Okay? It's a minus 1/8 then. But, so you can do that. So much easier to change your limits most of the time. Okay? And that gave you the same result. All right. Now, how are we doing on time? Not much time here. What's that? 6 minutes? Okay, great. Trying to find. We just did example 8. Examples 9, the top of the page. Oh, no. Let's do example 9. Okay, that's probably. Don't know if we're going to have time for it or not, but let's give it a shot. Evaluate this definite integral. Integral from 1 to 5 of x divided by square root of 2x minus 1 dx. Okay. Now, there's any one of a couple of approaches to how to do this. How would you like to do it? I'll let that be your choice. Second?
U equals 2x minus 1.
Yes, that's exactly how I'd start it. Let u equal 2x minus 1. Okay? That's always followed by then. Is what? Du is equal to 2dx. Is that what you said?
Yes.
Absolutely. Okay? And here we find our first problem. We have a 2dx down here, but up here we have an x dx. We've run into that before. How did we handle it? It was a long time ago, I realize. Maybe an hour. Any ideas? So this may take us into next time. So I may not run over time-wise, but anyone got an idea?
Solve for x.
Ah, right here. Right here. We solved for x. Yes. We did that. In fact, it's almost the same problem. What did we do?
Add 1 to both sides.
Add 1 to both sides. And you get 2u, no, I'm sorry, u plus 1. Let me get rid of that 2. It's ugly, ugly, ugly. Okay, u plus 1 is equal to 2x, but we don't want 2x, we want x, so divide by 2, and that gives us x equal u plus 1 over 2. All right. Now, down here, we're also going to want to divide by 2. Okay, so the dx is going to be du over 2, and the x is going to be u plus 1 over 2. Okay. So, my new integral is going to be, here I have an over 2, there I have an over 2, so we have a total of an over 4 here. So we'll do a 1/4 out front. And we'll do the integral with no limits yet. And what else do we have then? I pulled the 2 out front, so that x with the 2 out front is 1/2 out front is going to be a u plus 1, and the dx is going to be a du over, and what's your denominator here? Second? What's your denominator? What's it? U to the 1/2. All right. I really don't like the way that looks, but before I do anything about changing the way it looks, I want to change my limits. And remember, here is the key formula for changing the limits. I was marking all around it to try to get your attention on it earlier. But when x is equal to 1, what is u? It's what? It's 2 times 1, which is 2, minus 1, which is 1. Right? Amazing but true, right? Okay. When x is equal to 5, though, what is your u? It's what? 9. Perfect. Now we've got it set up well. Okay. So we may be able to finish this. I'll write that from 1 to 9. Those are the limits for u now. I don't want that u to the 1/2 in the denominators. Where do I choose to put it? As what? U to the negative 1/2 times u plus 1. And that's times du. Okay? Same thing we did before. Integral from 1 to 9. And what would you do with that then? This isn't quite the same problem before, but it's similar. What would that be?
Distribute.
Second, distribute, yeah.
So u to the 1/2.
U to the 1/2 plus u to the minus 1/2. Okay, du. And I think we can do that integration. Don't have much room to do it, but let's do it up here. It's 1/4. What's the antiderivative of u to the 1/2? Not that hard. What is it? What is it? Antiderivative of u to the 1/2. Help me, somebody. U to the?
2. Let's see.
Yeah. 2/3. U to the 3/2. And this one would be plus
2u to the 1/2.
2u to the 1/2. And then evaluate that from 1 to 9. Thank you for those limits, because those are going to work out nicely. This will be 1/4 times, okay, let's plug in a 9. Now, you have to remember a couple choices here. I always, especially if it's a perfect square here, let's do the square root first. The square root of 9 is 3. 3 cubed is 27. I want to divide the 27 by the 3 that's down here. 9 times 2 is 18. So that first part is going to be an 18. Now, I know that was a lot of, oh, and we got a plus here. Okay, then we do the same thing with the second part, and that's plug in a 1. Oh, square root of 1 is 1 times 2 is 2. So that part is a 2 there. But now we have to do our subtracting of those same things from when you plug I'm sorry, I did that wrong. Whoa, I really did it wrong. I was doing the second part, but not subtracting. You plug the 9 in here. 2 times square root of 9, that's 3, that's a 6. That's a plus 6. I'm in a hurry, so I was trying to rush, and I was screwing it up. Okay. Notice we put a 9s first, now put in the 1s. Okay? And that's going to be a 2/3, right? Because 1 to the 3 halves power is 1. So that's 2/3 minus, and 1 to the 1/2 power is 1. So that's going to be a 2. All right. A lot of ugly mess here. This is going to be 24 minus 2 is 22 minus 2/3 would be 21 1/3, which is going to be 64/3 times 1/4. And 4 going to 64 16 times. So I think it comes out 16/3. I hope it does. Yes, it does. Good for them. We've run out of time, haven't we? Way out of time. Devin, you were supposed to keep me from going over, weren't you? Never mind. Okay. If we need to come back and do some of that later, or if you have questions, I'll answer them now. You okay with it? Tell Jake we went over, but there's no extra charge, so when he listens to this. All right. Okay. Any questions on that? All right. That was example 9, and we did get the 16/3. There is a little blurb at the bottom of the page that's not on the slide set. It's talking about geometrically and interpreting this. And frankly, that's what we've always done, so I don't really see a big reason to do much about it. We'll start next time with the next slide, which is that one. No. That one. Integration with even and odd functions. Okay. Almost finished 4.5, which means we're almost finished with Chapter 4. Homework exercises, any of either 5 or 7. They're both at Calc Chat. 5's at Calc View. Any of the odds, 9 through 29, they're all at Calc Chat. 15's at Calc View. Either 31 or 33, both at Calc Chat. 31's at Calc View. 35's at Calc View. 37's at Calc View. Calc View. No, Calc Chat. They're both at Calc Chat. Sorry. 35 and 37 at Calc Chat. Any of the odds 39 to 47, all at Calc Chat. 45's at Calc View. Either 49 or 51, both at Calc Chat. 49's at Calc View. Any of the odds 53 to 59, they're all at Calc Chat. 53's at Calc View. Any of the odds 61 to 67, all at Calc Chat. 65's at Calc View. 69 or 71, both at Calc Chat. 69's at Calc View. Goodness gracious, we'll stop there. Actually, those last two are the regions under a curve, which is exactly what we were doing, but they didn't have an example. They just had a discussion. If you can't get that at the bottom of the page, they don't have it in the slide set, but it's exactly what it is. You know, you're just doing the area under curves. If you can't get those, ask me and we'll work some of those in class. We'll start next time with even and odds. And then we'll move into Chapter 5, okay? But we'll finish Chapter 4 first, which will only have one more page to do. Then we'll move into Chapter 5 and get as much of that done as we can. Okay, for those who came in a little later, we have class through next Monday. We have it Wednesday and Monday. Final start technically on Tuesday, but I'll give you your final Monday afternoon, Monday at the end of class, and you have at least a week to work on it. Any of you who came in late graduating this term? Okay, then you'll have until Monday the following week to turn it in. But if you're graduating this term, you got to have it in to me by Thursday of next week. Okay, good deal.
Is it going to be cumulative?
I'm sorry?
Is it cumulative? Is it cumulative? Like all? Is it cumulative?
Oh, no. The final is just going to be on Chapter 4 and 5. Sorry. Mostly on 4, but a little bit on 5. Whatever we get to cover. But I could make it cumulative. No, I'm just kidding. Okay. All right. don't know how I did that, but anyway.